Hi Year 13, Mr. Vinaud here again, going to walk through how to write the electron configuration of ions. This video follows on directly from the previous, which was called Electron Configuration of Atoms. Before I go in depth into writing it for ions, I thought I'd look at the periodic table and how that can be helpful for determining the electron configuration for atoms and ions. You can see here my simplified version of the periodic table. I've color-coded it into different sections. Now all of the elements that are in this red section here, their valence electron will be in an S subshell. That S block also includes hydrogen and helium. So any of the elements in here, for example sodium, potassium, rubidium, they all have their valence electron in an S subshell. All of these ones over here in the green block have their valence electrons in a P subshell. All of the elements in this block here have their valence electron in a D subshell. And those ones way down the bottom that we hardly ever use, they have their valence electrons in the F block. So just by knowing the position of the element on the periodic table can be very helpful for determining what subshell its valence electron is in. So let's look at a few examples now for how to write the electron configuration for various ions. I've got here two atoms and the ions that they form, and let's talk through how to write their configuration. So for sodium, its electron configuration is 1s2, 2s2, 2p6, 3s1. Its valence electron is in the third energy level in an S subshell. So I can determine its position on the periodic table would be third energy level S subshell, somewhere around about there. So when it forms Na+, that means it's lost an electron. It now has more protons than electrons. Specifically, it's lost one electron. That's why it has a 1+ charge. So we can see here, looking at sodium, that it has one electron in its valence shell, and the third energy level, the S subshell. So to form Na+, we simply remove the electron that is furthest from the nucleus. That's for forming any cation. We remove the electron that is furthest from the nucleus. In this case, that'll be the 3s1. So the electron configuration for Na+ will be 1s2, 2s2, 2p6. That configuration is the same as neon, the inert gas. Because we know that the inert gases have a stable configuration, that's why they don't react. And so most elements, when they do react, will form that inert gas configuration. Not necessarily of neon, but of an inert gas. Let's have a look at chlorine. Chlorine has the configuration 1s2, 2s2, 2p6, 3s2, 3p5. It has 5 valence electrons in that P subshell. We can see that it forms Cl-. That means it has gained an electron. It now has one more electron than protons. So if it's going to gain an electron, we can see that there is space in our P subshell because it can hold a maximum of 6. So when we form an anion, you simply add an electron into the outermost subshell. So that's going to leave us with 1s2, 2s2, 2p6, 3s2, 3p6. It's gained an electron in the outermost subshell, and that has now formed the argon configuration. So again, as an atom reacts, it forms that stable inert gas configuration, which we could express like this. Let's look at a couple of transition metals, because there's a slight exception that we need to remember when transition metals form ions. Being that they are metals, they form cations, meaning they lose electrons. And a lot of the elements in the transition metals can form ions with multiple different charges, or they're in different transition states or oxidation states. So let's have a look at Fe, for example. Fe is element number 26. So its configuration would be the argon configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6. Then we would add on 4s2, 3d6. That's the electron configuration for iron as an element. Now you can see it forms two different cations there, one with a 2+ charge, one with a 3+ charge. Now the general rule is we lose an electron from the furthest orbital from the nucleus, and that is by distance, not by how much energy the electrons contain. So in this case, the fourth energy level is further from the nucleus than the third energy level. So we will always lose the 4s electrons before we lose the 3d electrons. So let's apply that now to Fe2+. Fe2+ will have lost 2 electrons, so those 2 electrons are both going to come from the 4s subshell, because that is the subshell that is furthest from the nucleus. So if we remove both of them, that leaves us with just 3d6. So that would be the electron configuration for Fe2+. Forming Fe3+, we can see that we need to lose 3 electrons. So again, we would lose those 2 from the 4s subshell first, and then we need to lose a third, and that third electron would then come from the 3d subshell, leaving us with the Argon configuration 3d5. So that's how to write the electron configuration for ions. I hope you found this video helpful. Cheers.